All right, yeah, hi students, very good evening everyone. Very good evening everyone. Okay, yeah. All right, so sorry for a slight delay, some technical issue, but yeah, now we are live with the control system. Next session, all 2 marks question. The previous session we had 2021 to 25 EE and EC. Okay, control system, all 1 mark question, and this is going to be all 2 marks question. Good evening Manju, good evening Dinu, good evening Dharun, very good evening everyone. All right. Session, all 2 marks question. The previous session we had 2020. Thank you Dharun. Good evening Nutan. All right, so quickly update all your friends that the session is live and we can get started now. All right, dear students. Okay. All right, so moving ahead and starting our discussions. Okay, the first question for the day. Okay, let us move ahead with the first question of the day. Okay, GATE 2022 EE 2 marks question. So as the session clearly says that today we are going to discuss anyways all 2 marks questions. Okay, previous session we had all 1 mark question. So this is the new theme that I thought of discussing with you this time. Okay, subject wise, recent year question, ECE common subject. So taking combined questions and recent year, which gives you the more analysis of the trend and the difficulty level of the GATE examination, and all 2 marks question to be taken today. Right. Good evening Maheshwari. Okay. So here it is, the first question for you, a simple one. Okay, so some questions for 2 marks can also be actually simple, but some good questions also you will be finding in the session. The damping ratio and undamped natural frequency of a closed loop system as shown in the figure are denoted as zeta and omega n respectively. What are the values of zeta and omega n? What are the values of zeta and omega n? So let's see this. Okay, it's a very simple question. You just have to get the characteristic equation. For that there is some inner loop. Okay, let me only solve up the inner loop. What is the gain of the inner loop? G upon 1 plus gh. Okay, H unity feedback. Okay, so simplifying this, multiplying by S, so you get 10 divided by S plus 10. 10 is divided by S plus 10. Okay, now this particular inner loop is cascaded with 10 by S. So what is the overall characteristic equation here? The overall characteristic equation will be 1 plus complete loop transfer function. So what is there in the forward path gain? 10 upon S plus 10 multiplied by 10 by S. That's it. Equal to 0. HS is, for the final system also, HS is unity only. Correct, dear? Okay. So when you simplify this, S plus 10, that is S square plus of 10S plus 100 equal to 0. Problem solved. Very simple for 2 mark. Okay. Omega n square is 100. So omega n is 10. Okay. And then this term we all know is 2 zeta omega n, which is 10. So 2 zeta into omega n, which was already 10, is 10. 10 cancel. Zeta is 1 by 2. Okay. Zeta is 1 by 2. So zeta 1 by 2 and omega n 10 being option number A the correct answer. Simple. Option number A itself is directly the correct answer. Okay. You also keep solving and keep commenting, dear. Okay. Dinu says option number C. No, not C. Just recheck it. Okay. Okay, fine. It's a straightforward calculation coming out to be option number A. Okay. Okay, then let's move ahead to the next question. What is there? Consider a closed loop system as shown in the figure. Okay. 14.4 upon S, 0.1 S plus 1 is the plant transfer function. Plant transfer function means GP. Okay, and GCS equal to 1 is the compensator. Now see, they have just used the compensator, but what is the gain of the compensator is 1. That means there is no role of the compensator actually in this question. Okay, in fact, many questions you will find in the gate where they are using some sort of controllers or compensator, but eventually that question is either on the basics of transient analysis or steady state error analysis or stability analysis. There is no much role of the separate controller or compensator concept. Honestly, you will find such questions. Okay, so GCS is simply one. For a unit step input, the output response has damped oscillation. What is the damped natural frequency? What is the damped natural frequency? Omega d given by the formula omega n root of 1 minus zeta square. Okay, where GPS is given to you. What is this GPS? GCS is anyways 1. GPS is 14.4 divided by S into 0.1 S plus 1. Okay, correct. Right. So, yeah, I shall first write down the characteristic equation. What is the characteristic equation? 1 plus, okay, loop, this is simply 1. So, only there in the forward path gain is GPS, unity feedback. So, 1 plus only GPS to be taken. S 0.1 S plus 1 equal to 0. So, simplifying this, you have 0.1 S square plus S plus 14.4 equal to the 0. Multiplying by 10 actually, so that I get S square plus 10S plus 144 equal to 0. So, dear, once again, first I will get omega n square is 144. So, what is omega n for the system is 12. Okay, and then 2 zeta omega n is 12 equal to 10. So, zeta here will be, you can cancel 2 there. So, zeta can be 5 by 12, correct. Zeta here can be 5 by 12. Okay. So, the question is damped frequency of oscillation. Dinu has some answer 10.9. Okay. Okay, Dinu has some answer. Okay, yeah. So, then solving the final value, omega d, as I told you, omega n root over of 1 minus zeta square. What is the omega n we calculated is 12 under root of 1 minus 5 by 10 whole square. Okay, so 5 square 25 and 12 square 144. So, I can simplify this as 12. 144 minus 25 will be how much? 119, correct na? Right, divided by 144. Root 144 is again 12. Okay, so the only answer is root 119. Okay, root 119. Okay, let me approximately calculate this value. Okay, yeah, let me just do that calculation part for you. Okay, do I have the calculator here? Just a second. Okay, Dino has given some answer. Okay, so calculating, you calculate as always by the gate watch. Yeah, 10.908, correct. Okay, 10.908. So let me write it as 10.9. This is the damped frequency of oscillation. 10.9 radian per second is what is the correct answer. Okay, 10.9 radian per second. Round off to 2 decimal place. So, okay, I can then write down, being very using all precautions here. So, we can approximate this to 10.91, 10.908 what we got now. Dharun, correct answer. Okay, Dharun also has the correct answer. Okay. Okay. Next question then. What is there in the next question? Okay, so this is done already. Yeah, GATE 2022 ECE 2 marks MSQ question. Okay. Two linear time invariant systems with the transfer function G1 and G2 are given to you. Okay. They have unit step responses Y1t and Y2t respectively. Which of the following statements is or are true? Which of the following statements is or are true? Okay, now see, they have the same percentage peak overshoot, they have the same steady state value, they have the same damped frequency of oscillation, they have the same 2% settling time. Okay, 4 different options. So it's a MSQ question, so we just have to comment on both, but all of them ultimately depends on zeta and omega and a basic transient question. Okay, what is G1s? It is 10 upon S square plus S plus 1. What is here? S square plus S plus 1. So, be careful and write this as 10 into 1 upon S square plus, okay, because how do we write down the second order transfer function in general? S square plus S plus 1, this is what is given, and we generally write it as K into omega n square upon S square plus 2 zeta omega ns plus omega n square, correct? Right. So, when I compare to this, Okay, when I compare to this, what is the value? Okay, what is the value of k for this for G1? For the G1, k will be equal to 1. Okay, omega n square is 1, so omega n also 1. Okay, then 2 zeta omega n is also 1. Okay, so solving this further, 2 zeta omega n was anyways 1 equal to 1, zeta equal to 1 by 2. Okay, zeta. So let me call this as k1 omega n1 and zeta 1. Okay, similarly, G2s is given to me. Okay, what is the G2s given? 10 upon s square plus s root 10 plus 10. S square plus s root 10 plus 10. Okay, so when you compare this to the original transfer function, see, this is omega n square and omega n square. That means k equal to 1 here. Okay, previous case k was 10. I think I written 1, sorry. This is k equal to 1. Let's say this is k2. Omega n square is 10. So omega n will be under root 10. Okay, and then last calculation, 2 zeta omega n is how much? 2 zeta omega n. The central coefficient is root 10. Dharun has come up with some answer. Okay, so that means 2 zeta into omega n is root 10 is equal to root 10. Cancel out. Zeta 2 is also 1 by 2. Okay, zeta 2 is also 1 by 2. Okay, now peak overshoot depends only on zeta. You don't have to actually calculate which of the parameters are same, so it's not going to be much calculated. The only thing we needed the zeta and omega n. So now see there, zeta 1 is equal to zeta 2, so definitely overshoot, peak overshoot for the first system will be equal to the peak overshoot for the second system. Okay, because overshoot only depends on e power minus pi cot phi, or expanding in terms of zeta, it is e power minus pi zeta divided by root 1 minus zeta square. It does not depend on omega n. Okay, it does not depend on omega n. Okay, then what is the next option? They have the same steady state value. Steady state value for unit step response is actually given by k. Okay, so k1 is not equal to k2. Okay, so steady state values, okay, are not going to be same. B option is wrong. Okay, B option is wrong. Okay, this was A option, this was B option wrong. C option, what is there in the C option? They have the same damped frequency of oscillation. Now see, omega n for the two system is different. Okay, omega d damped formula, the damped frequency formula, what we just used in the last question also is omega n under root 1 minus zeta square. Okay, zeta 1 is equal to zeta 2. No problem, but omega n1 is not equal to omega n2, correct na? For the first system, the omega n was how much? 1. For the second system, it is root 10. Okay, so since omega n is different, although zeta is same, the omega d also will be different. Omega d1 will not be equal to the omega d2. The C option also wrong. Okay. What is the last option? They have the same 2% settling time. What is the settling time formula? Settling time formula, 2% settling time formula, 4 by zeta omega n. Okay, zeta is same point. Okay, zeta 1 is equal to zeta 2, but omega n1 not equal to omega n2. Settling time depends on both, so settling time 1 will not be equal to settling time 2. So only what is the parameter they have same? Okay, the same percentage overshoot, because the zeta was same. So what is the only correct answer? A. See, it is MSQ question. I have told you in earlier sessions also. Here also you see, and a few more examples today itself you will see where they have put it as MSQ question from control system, but only one option correct. Only one option correct. Okay. So yeah, correct. That is what Dinu and Dharan has given the correct answer. That is equal to A. That is equal to A. Next question. Okay. A closed loop system is shown in figure where k greater than 0, alpha greater than 0. What is the steady state error due to unit ramp input alpha by s square? Due to the unit ramp input alpha by s square. Very simple question actually. Okay. See, unity feedback is there. Okay. And what is the GS k upon s plus 2? Okay. How many poles at origin? One pole at origin. So what type of system? Type 1. Okay, the number s power 1, the number of poles at origin equal to 1. Okay, now for the type 1 system, what is the steady state error due to ramp input alpha by s square? Okay, due to unit ramp input, steady state error is actually given by 1 upon kV. But due to ramp input having the coefficient alpha, because unit ramp input Laplace is 1 by s square, it is alpha by s square, so steady state error will also be multiplied by alpha. Okay, so steady state error is actually alpha divided by kV. Okay, what is the value of kV? kV is given by the simple formula limit s tending to 0 s into gs. Okay, So this becomes limit of s tending to 0, s into k by s plus 2. SS cancelled, s tending to 0, answer is k by 2. Answer is k by 2. Okay, putting down the value alpha upon kv, kv is k by 2, putting the 2 above, so you have 2 alpha divided by k as the answer. 2 alpha divided by k, option number A. 2 alpha by k is the correct answer. Correct, dear? Yes, option number A correct again, Dinu. Yes. Okay, this was very simple, provided 2 marks. Next question, 2022 ECE 2 marks question. The block diagram of a closed loop system. Block diagram of a closed loop control system is shown in the figure. Rs, Ys and Ds are the Laplace transforms of the time domain signal Rt, Yt and Et respectively. Let the error signal be defined as Et equal to Rt minus Yt. Okay, assuming the reference input Rt equal to 0, the steady state error E infinity due to unit step disturbance. Okay, the error, steady state error due to unit step disturbance. Okay, so that means they want to take dt in the question as ut, or if you convert to the s domain, ds will be equal to us. But error as a standard definition is always defined as the difference between reference input and obtained output. Okay, so see here, come to this part here. Okay, error is Rt minus Yt. Okay, but Rt to be taken as 0. So what is the error signal is minus of Yt, or converting to the S domain, you can write down the error signal is minus of Ys. Okay, right. What is the Ys here? For a moment, consider this gain as G. Later we will substitute. Okay, later we will substitute. Okay, so what is there? You have to take R0. Okay, so see what is coming here, Y. Okay, and since R is 0, what goes here is 0 minus Y. Okay, that means this signal is simply minus Y. This signal is simply minus Y. So what I get here multiplied by 10, this is minus 10Y. This is minus 10Y. Okay, so you can get the Y expression simply. What is the value here? Okay, D minus 10Y, correct? Okay, input into gain is the output. Okay, so what is the input to this block? 10 minus D minus 10Y into G. Okay, so if you want to combine Y terms on the left side, you can take Y common on the left side. 1 plus 10G will come is equal to D. Okay, so Y output is D upon 1 plus 10G. It is equal to D is divided by 1 plus 10G, correct? Okay, so what is the error signal in that case? Okay, what is the value of the error signal? The error signal is then given by minus of Ys, that is minus of Ds is divided by 1 plus 10Gs. Okay. Right, Dinu has some answer 0.9. Okay, we shall check it. Okay, now we'll substitute the values. Okay, what is the steady state error, dear? The steady state error, okay, as we know, is the limit t tending to infinity Et, or by the final value theorem, it is limit of s tending to 0, s into Es. Now I'm going to substitute the data. Limit s tending to 0, s into Es. What is the error signal? Minus of ds. Minus of ds. ds is 1 by s. Okay, upon 1 plus 10g. 1 plus 10 into g. What is the g? Okay, 1 upon s, s plus 10. I'll substitute this now. 1 upon s, s plus 10. Okay, 1 upon s, s plus 10. Okay. So what is going to be in the numerator, s and s definitely getting cancelled. Okay, so this is limit of s tending to 0, s and s cancelled, minus, let me multiply by s, s plus 10 throughout. Okay, let me multiply by s, s plus 10 throughout. It is only 1 upon s, s plus 10. Na? Let me just recheck the calculation. That is 10g. D is divided by 1 plus 10g. Oh, sorry. A parameter I missed here. This is g also there. Gd. Okay, so y is equal to d into g, or g into d. Let me call it as dg. So that will come here also. ds multiplied by gs. Okay, ds multiplied by gs will come up here as well. Okay, so this particular term gs will also come up here. Okay, that is 1 by s, s plus 10. Okay, so this s getting cancelled, and now I will multiply by s, s plus 10. Minus is anyways there. So minus 1, then denominator s, s plus 10 plus 10. Now you put s tending to 0, so minus 1 by 10, minus 0.1. minus 0.1. Check it out, Dinu, once again, please. Minus 0.1 is the answer that is coming up. Okay. Correct? Minus 0.1 is the answer that is coming up. Minus 0.1. Okay. Next question. 21 EE 2 marks question. Okay. Again, this is a good question. Again on error analysis. In the given figure, plant GPS is 2.2 upon 1 plus 0.1s, 1 plus 0.4s, 1 plus 1.2s. This is GPS. And the compensator GCS is K 1 plus ST1 upon 1 plus ST2. Okay. The external disturbance input is DS. Again, the disturbance input is given. It is desired that when the disturbance is unit step, okay, it is desired that when the disturbance is unit step, the steady state error should not exceed 0.1. The steady state error should not exceed, okay, 0.1. So steady state error should be less than 0.1. Okay, should not exceed 0.1. Okay, what is the minimum value of K? Okay, where K is what is there in the compensator transfer function. See, again, this question uses some compensation, but not required. It is an error. If you know error analysis, this is some system with some transfer function. That's it. Okay, that's it. That's what you have to take. Okay, but again, you know, when the disturbance input is applied, what is the error? Okay, what is the error signal? See, in the previous question, if you notice, they clearly mentioned error is RT minus YT. Here also they have clearly mentioned that the error signal in block diagram is RS minus the output. Okay, that is output is CS actually. This is a typo error. Output is CS. RS minus CS. Okay. And even if not mentioned, by default the error definition is reference input minus output, obtained output. Okay. So this is what is given. Now I will have to take R equal to 0 because I am going to calculate the error due to the disturbance signal, which is unit step, that is 1 by S. So what is the error signal now? Once again, if R is 0, it again becomes minus of output, minus of C. R minus C, but R is 0. Clear? Okay. So now what is the flow of the variable this time? This is minus C into GC. Okay, minus C into GC. Okay, input into gain. Okay, so what comes up here? The disturbance signal D minus C into GC, then further multiplied by GP will give you the final output. This is CS, as I told you. Okay, so yeah, just writing the C equation. Now see here, what is the C equation? Gain of the system GP multiplied by what comes to the system? D minus C into GC. Okay, so again I will shift the C terms to the left. I will get 1 plus GC into GP. Okay, is equal to D into GP. Okay, is equal to D into GP. Correct? That also you can do. You can convert to SFG to find the error function, but not required. It's easy. If you just write down that equation, I think easy. This is what usually I follow. Okay, right? Okay, dear. Okay. Why this blink is coming? I think guys, just there is some glitch in the video, it seems. Hello. Just a second here. Okay, yeah, there was some sort of blink. I also noticed it, but hope that is fine now. Okay, looks fine only now. Okay, but in case of any issue, you let me know. Okay, yeah. Chalo, so what is the analysis here? Okay, so this is what we have done. Okay, right. So what is the C function? And error is going to be minus of C. So as I told you, error is minus of C, and minus of C means minus DGP upon 1 plus GC into GP. Okay, the question is steady state error again. Okay, the question is steady state error. It should be less than 0.1, should not exceed 0.1. Okay, should not exceed. I mean, it can be 0.1. It should not be greater than 0.1. So less than or equal to 0.1. Okay, but first here, let me calculate the steady state error. Okay, again, directly writing the final value theorem. Limit s tending to 0, s into error signal. Okay, substituting the error signal here. Limit s tending to 0, s into the error signal. What is the error signal we have got? The error signal is minus dgp minus d. What is d? Is 1 by s, unit step disturbance. What is gp? Okay, gp I will substitute then. Okay, this is the gp and this is the gc. Okay, 2.2 upon 1 plus how much? I'll just see once again. 0.1, 0.4, 1.2. 1 plus 0.1s, 1 plus 0.4s, 1 plus 1.2s. Divided by, what else is there in the error signal? 1 plus GCGP. 1 plus GC. GC is K into 1 plus ST1 divided by 1 plus ST2 into the same transfer function. 2.2 upon 1 plus 0.1s, 1 plus 0.4s, 1 plus 1.2s. Okay. Now you see, first of all, S and S will get cancelled, and again I will multiply by this entire denominator term. Okay, so what I am going to get is limit of s tending to 0 minus of 2.2 divided by 1 plus 0.1s, 1 plus 0.4s, 1 plus 1.2s. All of these terms are actually going to become 1, just writing it for your sake. Okay, plus 2.2k 1 plus st1 upon 1 plus st2. This is still left. Okay, now put down the s tending to 0. How much you get? Okay, if you put s tending to 0, you have minus 2.2 upon 1 into 1 into 1 plus 2.2k 1 upon 1. That is simply 2.2k. Okay, so the error is actually minus 2.2 upon 1 plus 2.2k. Correct, na? Okay, so what can I then say? What can I then say? Steady state error, which is equal to minus 2.2 upon 1 plus 2.2k. This should be less than equal to 0.1. That is what they have mentioned in the question. Na? Okay, so, okay, dividing by 0.1. Okay, so I have minus 22 less than equal to 1 plus 2.2k. Okay, or 2.2k will be greater than equal to minus of 21. Okay, 2.2k is greater than equal to minus of 21. So what is the value of k? Okay, is greater than equal to, okay, if you divide, what is the value you'll obtain? Let me calculate how much it is. 21 is divided by 2.2. 9.55. K should be greater than equal to minus 9.55. This is what is coming? Yes. Okay, so what is the question was asking, what is the minimum value of k? Okay, greater than equal to this value, so minus 9.55. K is minus 9.55. The minimum value of k is minus 9.55. Okay, because in the question they didn't mention that k has to be positive, negative. Okay, they have not mentioned, so k could be negative, and yeah, this is how it is. Tell me any doubts, if there's any doubts. Okay. Okay, next question, here it is. Let GS be given to you 1 upon s plus 1 s plus 2. Okay, let GS be 1 upon s plus 1 s plus 2. Then the closed loop system shown in the figure below. The closed loop system, a very simple question exists. Okay, if I directly want to write down the characteristic equation for the system now, what will be the characteristic equation? 1 plus loop transfer function, that is k s minus 1 into GS. GS I will substitute as 1 upon s plus 1 s plus 2 equal to 0. So multiplying by s plus 1 s plus 2 throughout, what do you get? Okay, multiplying by s plus 1 s plus 2 throughout, s square plus 3s plus 2, then plus ks and minus k equal to 0. Okay, that means you have s square plus combining the k term, k plus 3 into s, and then plus 2 minus k equal to 0. Do you need any Routh-Hurwitz? No. In the previous session also we discussed some Routh-Hurwitz based cases. Now here no Routh-Hurwitz required because it is second order system. Okay, it is a second order system. Okay, now because it is second order system, what I told you for second order system? Okay, of course for higher order Routh-Hurwitz would be required, but for second order system, if all coefficients have the same sign, the system will be stable. okay, the system will be stable because it is second order. Okay, so what you need, k plus 3 should be positive because this is positive. So k plus 3 should be positive and 2 minus k, this is 2 minus k, na? 2 minus k must be positive. Okay, that means k greater than minus 3, and from here you will get k is 2 greater than k is less than 2. So system is stable, okay, for this range, minus 3 less than k less than 2, greater than minus 3 but less than 2. Now choose the correct answer. Greater than minus 3 but less than 2. Okay, now you can choose the correct answer here. Okay, so what is going to be there? Is it stable for all k greater than 2? No. Actually, for all k greater than 2, it is unstable. Answer is B. Because for stability, k should be less than 2 and up to minus 3. Okay, sometimes in the question they can mention k should be positive, then if they mention k positive, then the range of k is still 0 to 2. But for any k greater than 2, system is unstable. So B option is suitable here then. B option is suitable. Okay, simple one. Okay, gate 25, ECE 2 marks. Okay, again a decent question. Okay, again a decent question. Okay, just a moment. Yeah. Okay. Chalo. What is there? I already commented on your doubt, Dinu, na, earlier. Okay. So have a look into it. Let GS, this is the GS, be 1 upon 10s square, be the transfer function of a second order system. A controller MS is connected to the system in the configuration shown below. Consider the following statement. There exists no controller of the form Ki by S, where Ki is a positive real number, such that closed loop system is stable. Okay, integral controller. Okay, pure integral controller without proportional part. Okay, see, I will show you, but if you generally remember basic conclusions, that anytime if you use pure integral controller without the proportional part, it will always tend, it is always going to make the system tend towards instability. Okay, tend towards instability. But okay, what is there in the first statement? What is going to be the characteristic equation? You can solve it up simply. In the first case, characteristic equation will be, see, characteristic equation is how much? 1 plus ms into gs. This is there in the loop transfer function. Unity feedback is there. Okay, what is the ms? Okay, Ki by S into what is the GS? GS is given as, yeah, GS is given as 1 by 10s square and equal to 0. Now you clearly see 10s cube, you simplify, plus Ki equal to 0. Okay, what happens? S square, S power 1, missing terms, and whenever you have missing terms, necessary condition fails. No need to go for Routh-Hurwitz analysis. Okay, the first thing is, for higher order system like third or fourth or higher order system, okay, all the coefficients of the characteristic equation must be of same sign and all must be present. None of them should be absent. If the necessary condition satisfied, then we go to the sufficient condition, which is in the form of Routh-Hurwitz. Okay, Routh-Hurwitz. Okay, so what is there? Missing terms are there. The system can't be stable. Okay, system can't be stable for sure. Okay, so what is the first statement? There exists no controller of the form such that a closed loop system is stable. True. Okay, for any value of Ki, the system cannot be true. The system cannot be stable. So this is true option. Okay, then there exists at least one controller of the form Kp plus Skd. Now you see dear, I am telling you, most 99% of the questions of controller compensator are more towards the basic idea, either about stability or transient formulas or error formula. Okay, even if you don't know this is integral controller, what is there? Some gain is given. What is this? Okay, Kp plus Skd. Those who have studied, they must know this is a PD controller. Those who have studied, they must know this is a PD controller containing the proportional part and the derivative part, proportional derivative controller. But even if you don't know this, no problem. Some gain is given. Okay, I will put down this in the characteristic equation. What is there? I will put this in the characteristic equation. 1 plus Kp plus Skd, that is the controller gain, multiplied by the plant gain, 1 upon 10s square equal to 0. Now I have 10s square multiplied throughout, then here Kp plus Skd, or let me reverse and write Skd plus Kp equal to the 0. This is what is there, correct? Okay, 10s square plus Skd plus Kp equal to the 0, correct? Now there exists at least one controller of this form, okay, so that the system is stable. Now see, this is a second order system. This is a second order system. All coefficient must be of the same sign. Okay, this is already plus. So this can be stable if KD as well as KP are chosen to be positive. Because already you start with positive, so these two terms should also be positive. So yes, okay, not only one, there can be multiple controllers. I think some video issue is happening there. No, it is fine now. I think it was stuck, but fine. Okay, there can be multiple controller. I mean, you can choose any value of KP, KD positive. Okay, the system remains to be stable. Okay, the system remains to be stable. That is what is there. Correct? Okay, so the second statement is also correct. What is there in the second statement? There exists at least one controller of this form. Yes, multiple controller. Choose any value of KP, KD. Okay, so second is also correct. So correct answer is option number D. Both the statements are true. Basic error analysis. Oh, sorry, basic stability analysis. Correct? Yes, the Sampath correct answer D. Sampath correct answer. It is D. Okay, fine. Consider the polynomial s power 5 plus 7s power 4 plus 3s cube minus 33s square plus 2s minus 40. Okay, there is a fifth order polynomial given. Let LIR be defined as follows. L is the number of roots of PS with negative real parts, that is the number of roots in the LHP. I is the number of roots of PS, that is pure imaginary, the imaginary roots, and RS is the number of roots of PS with the positive real parts. Okay, with the positive real parts. This is what has to be taken. Okay, which one of the following option is correct? That means we need to calculate the value of L, I and R. We need to calculate the values, these values, that is the L, I, R values. Okay. Just a second here. Okay, yeah, I think that is fine now. Mostly some, other than that maximum phase lead or the frequency at which maximum phase lead occurs, some basic questions with respect to Bode plot analysis or some direct, conclusive questions, the conclusion, general effects of the controllers and compensators, as well as basically identifying lead or lag compensator. That is also important. Lead compensator, lag compensator, or lead lag or lag lead. That is also one important area from compensator. Okay, yeah, so let's start solving this. Okay, fifth order polynomial is given, so we have to go to the Routh-Hurwitz. Definitely the system will not be stable. Okay, minus sign. Okay, necessary condition failed, system can't be stable. So if they asked about stability, we can say the system cannot be stable, but they are not asking about stability. They are asking about how many roots in the left, right and imaginary axis. So for that we have to do the analysis. Okay, we have to do the complete analysis starting with s power 5 and s power 4. Okay, s power 5 alternate coefficients will be 1, 3 and 2, right? I have 1, I have 3, I have 2. S power 4 coefficient 7 and minus 33 and minus 40. 7 and minus 33 and minus 40. Okay, this is what it is. So now s raised to the power 3. 21 minus of minus 33 will become how much? 54 by 7. Then 7 to 14 minus 40, this is also 54 by 7 and then 0. Okay, so what can I do? Rather than writing 54 by 7, first of all cancel this 7. I mean multiply throughout by 7. Okay, we can, for any particular row we can multiply or divide by a particular number. Any particular number that should be positive. Sign change is not allowed. So s power 3 I am writing as 54, 54 and 0. Okay, now going to the s power 2 row. Okay, so what is there in the s power 2? Now you don't count this. Okay, so 54 into minus 33 minus 7 into 54 divided by 54. Okay, so anyways 54 will cancel, na? What is the number I am telling? 54 into minus 33 minus 54 into 7 divide by 54. So only minus 33 minus 7 minus 40 will come. Okay, what is going to be the next number? Now 54 into minus 40 divided by 54 minus 40 and 0. Then s power 1 row. Okay. Okay, what is there in the s power 1 row? Now you see, okay, both these rows are identical. Okay, right, 54 minus 40, 54 minus 40. So the value of this determinant 0. This is anyway 0 because the next column on the top is 0. Last element of a row in Routh-Hurwitz is always 0. Okay, so you have a row of 0. Okay, ROZ case, the most important expected case from the Routh-Hurwitz is about ROZ. So you have ROZ. And whenever there is a ROZ, we form auxiliary equation from the row above the row of 0. What is the auxiliary equation? Minus 40 s square minus 40 equal to 0. Or you can cancel out 40 minus s square minus 1 equal to 0. Don't cancel out the minus sign. Sign changes are the most important thing. Okay. Minus s square minus 1 equal to 0 and then differentiate the auxiliary equation. So what do you get? Minus 2s equal to 0 and hence you get the modified s power 1 row. Okay, now I will write down the modified s power 1 row. What is there in the s power 1 row? The modified s power 1 row, which is obtained by the derivative of auxiliary equation. The coefficient is minus 2. S power 1 coefficient minus 2, remaining 0, 0. Now continue with the Routh array. So last row left, s power 0, minus 2 into 40 upon minus 2. So minus 40 is coming and 0, 0 is coming. Okay, 0, 0 is coming. Okay, so what is going to be the answer? Okay, what is going to be the answer? Right. So if you are looking for a text, Sampath, you can cover it from Benjamin Co. Okay, you will get sufficient insights. Now you see very, very clearly, okay, very, very clearly how many sign changes are there? Plus, plus, plus to minus. This is the only one instant sign change, then minus, 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 minus. Okay, so what is there? Only one sign change. Okay, only one sign change. So how many roots in RHP? 1. Then how many roots in imaginary axis? See, imaginary roots can only come due to auxiliary equation, otherwise not. And here auxiliary equation is simple, so we can simply solve it. Okay, what is going to be the auxiliary equation? To solve it, you will get what? Minus s square is minus 1. So s square is minus 1, s equal to plus minus j. Yes, you have a pair of imaginary root. Every root of auxiliary equation is also a final root of the characteristic equation also. How many imaginary roots? 2. So how many for LHP left? It is a fifth order equation. 1 goes to the RHP, 2 on the imaginary axis. So remaining 2 on the left LHP. Okay, so what is the correct answer? L2, I2, R1, option number A. Option number A. Okay. Any confusion, you can update me. Okay. Okay, consider an even polynomial Ps equal to s power 4 plus 5s square plus k plus 4 plus 4 plus k. Okay, the complete range of k for which Ps has all its roots on imaginary axis. Now see, Ps has all its roots on the imaginary axis. Okay, imaginary roots come. Okay, now what is the method number 1? I'll tell you a simple logical method for this question. What is the method number 1? Okay, if you want j omega imaginary roots can only come if there is an auxiliary equation, and auxiliary equation is related with the row of 0. When you are forming the Routh array, it should have a row of 0. It will have if you start forming the Routh array. That anyways everybody can do. The Routh-Hurwitz method you can all do. Okay, what is a simple method I want to present here? Okay, the range of k for which all roots are on the imaginary axis. Ps has all the roots on imaginary axis. Okay. That is what they want. All the roots are imaginary. Okay. Say all the roots are of the form s equal to how much? S equal to jy. Okay. Now, if all the roots are imaginary of the form s equal to jy, okay, what is the value of s square? Dear, what is the value of j square? Is minus 1. Okay, so s square is minus y square. That means s square is minus y square. So s square is a negative real number. I'm solving it by basic aptitude logic rather than going to the Routh-Hurwitz detailed calculation, which may take some time. Okay. Okay. Yeah. So the system definitely will not be stable here, Dinu. Okay, the system, see, when I say necessary condition fail, all coefficient of same sign should be there or none of the coefficient should be missing, that is necessary condition. But if necessary condition fail, what I told you, system can't be stable. So it may be marginally stable or it may be unstable. Remember that, you directly can't say unstable. Okay. Correct, Satyam. That is what we, how we form auxiliary equation, agreed. But I am telling you a basic aptitude logical method. Okay. Routh-Hurwitz, I am supposing we have done questions today, we have done in the earlier class also. I am just doing an alternate method. So s square will be a negative real number, minus of y square. Okay. Now, since this is an even polynomial, y s square will help me because this is an even polynomial, correct? Okay. The given polynomial is an even polynomial, only containing s square and s power 4 term. Okay. So, for a moment, in the polynomial, let me come up here. What is a polynomial given to me? What is a polynomial equation that I need to solve? S power 4 plus 5s square plus 4 plus k equal to 0. Okay. Put down s square equal to some number x. So if you put s square equal to x, s power 4 is x square. Then you have 5x plus 4 plus k or k plus 4 equal to 0. Quadratic equation. Huh? Now easily can't you solve quadratic equation? Okay, what are the roots of quadratic equation? What are the roots of quadratic equation? Minus b plus minus root over b square minus 4ac, okay, divided by 2a. So what is x coming out to be? Minus 5 plus minus under root of, solving this, 25 minus 16 will become 9 and minus 4k divided by 2. But what is s square is x, and already I told you about s square. S square is a negative real number. It should be negative real. Okay. So now see, what you want x to be real. There are two things. Okay. You want x to be negative real. So first x should be real. Okay. That means 9 minus 4k. The discriminant, quadratic equation discriminant 9 minus 4k should be greater than equal to 0, because if this discriminant is negative, under root of negative number will be imaginary quantity. That I don't want. Okay. So we get one condition from here. How much? Okay. 4k less than 9. So k less than equal to 9 by 4. Okay. Then x has to be negative also. Not only real, it has to be negative. Okay. So now see, what is the value of x? Okay, what is the value of x? You see here, I'll split this. There are two solutions now. Okay, minus 5, let me write down the first one, minus of 9 minus 4k minus of 9 minus 4k divide by 2. Now see, this is anyways going to be negative. Minus and minus will be more minus. Okay, but there is the other part, minus 5 plus under root 9 minus 4k by 2. Okay, now here there is a chance, if this is more positive as compared to this negative, answer will become positive. But if you want x to be negative, okay, the magnitude of negative number should be more. That is, 5 should be greater than under root of 9 minus 4k, or worst case equal. Now taking the square, 25 greater than equal to 9 minus 4k. Okay, or I can write down 4k here. Okay, how much? 4k here greater than equal to minus of 16. So k greater than equal to minus 4. K greater than equal to minus 4. So what is the answer? Greater than minus 4, less than 9 by 4. Okay, option number A. Greater than minus 4, less than 9 by 4. Option number A. Done. Na? By a quadratic equation logic, the question is finished. But yeah, you can try by Routh-Hurwitz. That ROC concept and auxiliary equation has to come. Okay, that I leave to you. That is the regular method. Okay, but just I wanted to show you some simple technique of going ahead to this question. Okay, all right. Then I'll have the next question here. consider a negative unity feedback control system with the forward path gain as shown. Okay, now see, this is a good question. GATE 2024 ECE 2 marks. This one is a good question. Okay, listen to me. Okay, there is a negative unity feedback control system with the forward path gain as shown. Okay, K equal to GS equal to K upon S plus 1, S plus 2, S plus 3. The impulse response of the closed loop system decays faster than, what is the meaning of this? Okay, right, impulse response of the closed loop system decays faster than e power minus t. Decays faster than, okay, now see, e power minus t, what is the Laplace transform? This is actually a question, okay, related to the concept what you study in the dominant pole concept. E power minus t, okay, has the Laplace transform 1 upon s plus 1, okay, and that is having the pole s equal to minus 1. Okay, now what you study in the dominant pole concept is the poles which are closer to the origin, or the poles which are closer to the imaginary axis in the LHP, they decay relatively slower. Okay, the poles far away from the origin, they decay relatively faster. Now I want the, okay, impulse response decaying faster than e power minus t. Okay, if you want impulse response, okay, decays faster than e power minus t, then you talk about S domain, then the transfer function should have the poles, okay, then the transfer function of the system, okay, should have poles okay, away from s equal to minus 1 towards more of LHP, because the pole which are away from origin, okay, so there is a reference pole minus 1. Now any pole which is more left of this will be definitely faster. Any pole which is right of this towards the origin will be slower. I repeat, that is what you study in dominant pole concept. Okay, if you go and revise the dominant pole concept, the poles closer to origin are relatively slower, the poles away from the origin are relatively faster. Okay, so transfer function should have the poles to the left of, okay, to the left of this particular pole, s equal to minus 1. The poles may be complex or real, but it should be left of minus 1. Okay, left of minus 1. Okay, so relative stability concept, shifting the origin concept of Routh-Hurwitz case will come. Okay, what is the current pole I have? I want the poles to be to the left of this. Okay, there is one pole at minus 1. Okay, I would just create a line, okay, parallel, a line passing through this one. Why I am taking an entire line? Because I told you, the transfer function should have the poles to the left of minus 1. Okay, not necessarily real. The poles may be complex also, doesn't matter, but it should be left of minus 1. Correct? It should be left of minus 1. Okay, so I want the poles in this zone. This is the allowed zone. Okay, poles must lie in this particular region. What is the region? Now this is a line. This is a line parallel to y-axis. Any line parallel to y-axis is given by the equation x equal to constant. X means sigma, the real axis. This is the x-axis, sigma axis, and this is the j omega axis. Sigma equal to constant. What is the value of sigma? Minus 1. Okay, so what is this region? Okay, the line is sigma equal to minus 1. You want to the left of the line, that means sigma less than minus 1. Okay, sigma less than minus 1. And poles means roots of characteristic equation. Roots of characteristic equation. Okay, so dear, whenever you want, okay, the number of roots, see dear, whenever you want the number of roots of characteristic equation, okay, to the left or right of a line, sigma equal to minus a, okay, right. To know the number of roots of characteristic equation to the left or right of the line sigma equal to minus a, okay, the procedure is, I am not deriving it, I am giving you the conclusion so that we solve more and more question. Replace s by s minus a in the characteristic equation. Okay, and then apply RH criteria. then apply the RH criteria. This is what is to be done. Okay. So dear, what is the characteristic equation for us? 1 plus GSHS equal to 0. See, GS is given, HS is unity. Let me just copy the GS, K by S plus 1, S plus 2, S plus 3. This is what is there. K by S plus 1, S plus 2, S plus 3. Correct, na? Okay, but what I have to do? Okay, I have to replace S by S minus 1. The value of A is 1 for us. The line is sigma equal to minus 1. Okay, right. So if you replace S by S minus 1, what is going to be your new characteristic equation? It will now look like 1 plus K by S minus 1 plus 1 will be S. S minus 1 plus 2 will be S. S minus 1 plus 3 will be S plus 2 equal to 0. Okay, so solving the cubic equation, you will get here S cube, then 1 plus 2, 3S square, 1 into 2, 2, 2 into S, and plus K equal to 0. Okay, K equal to 0. Right. Now you can apply the Rao theorem, S cube and S square. Okay, first row 1 and 2, and then the rest alternate coefficient is K and 3. Okay, 3 and K. Okay, so what is S power 1 row? 3 to 6 minus K. Divide by 3, last element 0. S power 0 row. Okay, suppose this is x, x into K by x. So what is going to be left? K and 0. Correct, na? Okay, so you want all the poles in the left. Okay, what you need? In left region. And whenever you need the poles in the left region, okay, not in the right region. So no sign change in the first column must be there. Okay, so if this is positive, positive, okay, if you want no sign change, so 6 minus A must be positive. Okay, that is K should be less than 6, and at the same time K should be positive. This also should be positive. Okay, so what is the condition? Okay, K should be positive but less than 6. K should be positive but less than 6. Okay, K should be positive but less than 6. Yes, Ritvik, the plan is there for signal and system also. Exact dates I'll update you, but similar session is also being planned for signal and system. Okay. Okay. So here it is. Now K should be between 0 to 6. The most appropriate option that will match is A. Okay. Between 0 to 6, so this is a subset of it. Okay. But here this is definitely wrong. Okay. This is pure negative, negative. No, only option number A. Okay. So this is satisfied. Okay. This is satisfied only by option number A. Only by option number A. This is the logic of solving the question. Okay, so see dear, I'll just repeat the point. Whenever you directly apply RH to a characteristic equation or to any polynomial equation, RH will tell you how many roots to the left or right of imaginary axis, j omega axis, sigma equal to 0 axis. Correct? If you want the number of roots to the left or right of a line sigma equal to minus a, okay, you simply replace S by S minus A in the characteristic equation and then apply Rautherwitz. Then whatever the answer given by Rautherwitz as per the sign changes, okay, like number of sign changes is number of root to the right. Right of what? Not imaginary axis. Right of this line sigma equal to minus A. Correct? Right? Correct. Next question. Okay, 24 EC 2 marks. This is also a decent question. Just a second. Yeah. Okay, read this question. Okay, a satellite attitude control system as shown below has a plant with the transfer function GCS cascaded with the compensator Cs, Ks plus alpha upon S plus 4, where K and alpha are positive real constant, in order for the closed loop system to have poles at -1 plus minus j root 3. Now, what is the intent of this question? Okay, see, now poles of the system, okay, at -1 plus minus j root 3. Okay, poles means roots of characteristic equation. Okay, what you need? Roots of characteristic equation at -1 plus minus j root 3. That means these are the two poles lying on the line sigma equal to -1, because the real part is -1. No? Okay, I'll show you with the picture again for any confusion. See, one method is what is related to the previous one. Okay, you want -1 plus minus j root 3. Now I am showing you this line. See this line here. Okay. See dear, again I take this line sigma equal to -1, real part -1. Okay, because how will you draw -1 plus j root 3? Okay, say this is root 3. So this is -1 plus j root 3, and say this is minus root 3. This is your other pole, -1 minus j root 3. That means this time you want the roots to lie on the line sigma equal to -1, not to the left, not to the right. Okay, so the question is like, find the value of alpha. Okay, question is like, find alpha, okay, so that roots lie on the particular line sigma equal to -1. So again, method number 1. Okay, again, I'll write it this here only as the method number 1. Okay, what is the method number 1? Find the alpha so that the roots lie on sigma equal to -a. Okay, again the same method. Replace S by S minus 1, because line is sigma equal to -1. Replace S by S minus 1, okay, in the characteristic equation, and then solve. Then solve by Rauterwitz, like the previous question. Now again, for this particular question, let me give you a basic aptitude approach. Okay, no need for any detailed calculation. See, why? Because they have given you the roots. Okay, poles. Poles means roots of characteristic equation. See how you can make this problem simple. What actually is the characteristic equation? Okay, method number 2 is simple logic. Okay, characteristic equation is 1 plus Cs into Gs. Write down the Cs, Ks plus alpha, Ks plus alpha upon S plus 4. Okay, is multiplied by Gs. Gs is 1 by S square. Gs is 1 by S square equal to 0. Solving it, you will get S square into S, S cube, then plus 4S square plus Ks plus alpha equal to 0. You want the root as -1 plus minus j root 3. Right? What is the question? The poles means root of characteristic equation. Okay, so, okay, S equal to -1 plus or minus j root 3 are the roots. Okay, if they are the roots of this equation, okay, they will satisfy the equation. They will satisfy the equation. That means when you put S equal to any one value, take any one value. Okay, some square and cube calculation, which I think will not be difficult for you. Put any one, -1 plus j root 3 whole cube plus 4 into S square plus Ks plus alpha equal to 0. Okay, so now real and imaginary part you separate. Right side 0. 0 means 0 plus j is 0. So put the real part to 0, put the imaginary part to 0. Okay, solve it. Okay, and after solving, put the real part 0, put the imaginary part 0. Okay, okay, solve and you will get. Okay, so calculations for this I will leave to you. Okay, solve and you get K alpha, both you will get. Okay, solve this as homework. A simple logical technique I have given to you. Because this time they have told you this is what the poles I want, so why not I will satisfy the equation. Simple. Otherwise, yeah, original method I have told you, the original conceptual method I have told you. Okay, but this again I have shown you in the previous question. Some basic logical thing I wanted to show you, because here exact roots are known. Previous question I wanted the roots to the left of the line sigma equal to -1. Here I want the roots on the line sigma equal to -1, that too with the imaginary part given. Even if I simply say the roots to lie on the line sigma equal to -1, then I have to apply the first method. But here exact roots are known. Sigma equal to -1 with the imaginary part known, √3. Okay, so we can just satisfy the equation. We can just satisfy the equation. Okay, just basic calculation is left. You can handle it. Okay. Okay, so please complete the value of k and alpha. Okay, complete this as the homework. Okay, we'll go to the next question then. Okay, yeah, this is again a good question by Rao-Hurwitz analysis. With some basic mathematical analysis will come. Question is on Rao-Hurwitz analysis. Just a second. Where is that gone? Just a second, dear. It is not moving. Yeah, this is the one. Correct. Yeah. Okay. A unity feedback. Okay. Keep looking into it. Okay. A unity feedback system that uses proportional integral controller. Okay. PI controller is shown in the figure. Okay. So now it is a proper PI controller, not pure integral. Kp plus Ki by S. Okay. This is Ki, dear. Kp plus Ki by S. The stability of the overall system is controlled by tuning the PI control parameters Kp and Ki. The maximum value of Ki, the question is, what is the maximum value of Ki that can be chosen so as to keep the overall system stable? Overall system stable, or worst case marginally stable. Okay, give the value, round off to 3 decimal places. Okay, you want to keep the system to be stable or worst case marginally stable. That means your system should not be unstable. Okay, so again, stability can be assessed by Rao-Hurwitz analysis, for which I need the characteristic equation. First of all, what is going to be the characteristic equation, dear, here? 1 plus Kp plus Ki by S, okay, multiplied by the Planck transfer function 2 upon S cube plus 4s square plus 5s plus 2. 4s square plus 5s plus 2 equal to 0. Okay. So, yeah, S Kp plus Ki can be written, and then you simplify and rearrange the term. S multiplied here. Okay, it will give you S power 4, then 4s cube, then 5s square, then 2s. Okay, then coming up here, S multiplied here, Skp plus Ki, and into 2 is left, equal to 0. So now let me rearrange the terms. S power 4, 4s cube, 5s square, total coefficient of S 2, and here Kp 2 Kp. Okay, 2 plus 2 Kp, then S common, and what is the constant term is Ki into 2. Okay, so that is 2 Ki. Any comments on stability can be obtained if you go to the Rao-Hurwitz analysis. Okay, if you go to the Rao-Hurwitz analysis, stability analysis can be then easily obtained. Okay, so I'll go to the Rao-Hurwitz. I'll first form the Rao-Hurwitz S power 4 and S power 3 row. Okay, what is there? Okay, alternate terms are 1, 5 and 2 Ki. 1, 5, 2 Ki. S power 3, 4 and 2 plus 2 Kp. This is 4 and 2 plus 2 Kp and 0. S square, now solving it, 20 minus 2, 18, 18 minus 2 Kp by 4. 18 minus 2 Kp by 4, or I can cancel 2, na? So 9 minus Kp by 2. 9 minus Kp by 2. Then 4 into 2 Ki by 4, 2 Ki. Last element 0. S power 1 row. Okay, S power 1 row, when I multiply these two, it will look like as 2 and 2 will cancel here. 9 minus Kp into 1 plus Kp. I take this 2 common and this is cancelled. Minus 4 to 8 Ki is whole divided by this term. Okay. 9 minus Kp by 2. Okay. This is going to be 0 because the next column is 0. Last element of a row anyway 0. Coming to the last row, S power 0. Suppose this is x. X into 2 Ki by x. So 2 Ki 0 0. Okay. 0 0. Correct. Now you want the system to be stable or worst case marginally stable. That means no RHP root. Okay. No RHP root means no sign change. Okay. No sign change required. Okay, no sign change required. Okay, so if you consider no RHP root, okay, so that means no sign change. So 9 minus Kp by 2, that means 9 minus Kp must be positive. So Kp must be less than 9. Then what is there? Even this particular time, 9 minus Kp this is already positive. So 9 minus kp into 1 plus kp minus 8 ki must be positive and 2 ki must be positive. Okay, so this tells you ki also must be positive. Okay, or worst case, okay, worst case, the system can be marginally stable. What they told? Worst case, system may be marginally stable. And now for marginally stable will always have j omega roots, a pair of j omega roots. Okay, and a pair of j omega roots will only come with the auxiliary equation, an even polynomial auxiliary equation. And auxiliary equation comes when you have a row of 0, ROZ in the Rauther-Width, and row of 0 comes in the odd power. Okay, so if you take the s power 1 row, that has to be 0. Odd power, see, s power 3 is the fixed row. This 4 you cannot make 0, but at least these two are 0. You can make this particular term as 0. So what is there? Okay, then you have to make 9 minus kp is multiplied by 1 plus kp minus 8 ki must be equal to 0. Okay, now when I put this equal to 0, see, I'll keep solving this equation further. Okay, what is this 9 minus kp? I'll rewrite this here. 9 minus kp multiplied by 1 plus kp. Okay, minus 8 ki is 0, or I can write this as 8 ki. Okay, so simplifying this, I will be able to write what is ki. Ki will be 1 by 8, and here if I solve 9, then 9 kp minus kp. So 9, then 9 minus 1, so 8 kp and minus kp square. Okay, the question is, for the system to be stable or worst case marginally stable, what is the maximum value of ki? I want the question of maximum value of ki. Okay, I want ki max, and for maxima, let's go to the derivative. D by, it is a function of kp, so d by dkp of ki. Differentiating this has to be equal to 0. Okay, so when I differentiate this, I will get 8 kp derivative 8 and kp square derivative will be 2 kp equal to 0. Solving this, you get kp equal to 4. And check that kp has to be less than 9. Correct, it satisfies. Kp should be 4. Okay, so correct, because kp has to be less than 9. Okay, so now put down this kp equal to 4. You will get the value of ki max. By second derivative, you can confirm it's going to be maxima. I'll just put down here the value. Okay, 9 plus 8 kp, kp was how much? 4, minus kp square, that is 4 square. So answer is 1 by 8 of 9 plus 32, this is 32 minus 16, 16 plus 9, 25. So answer is 25 is divided by 8, that is 3 and 1 by 3.125. The maximum value of ki, 3.125. Okay. So you will see, randomly sometimes some good question, basic mathematical analysis question out of control system coming up. Okay. That is why I have taken both the sessions. The previous session 1 mark, mostly all questions are directly achievable, but here some questions require the thought and the approach must be known to you. Okay. So 3.125 is the correct answer. 2021 ECE 2 mark question. Done? Okay. Moving ahead to the next question. Okay, here it is. Consider gate 24 EE2 mark question. Consider the closed loop system shown in the figure. Okay, with gs equal to k s square minus 2s plus 2 upon s square plus 2s plus 5. The root locus for the closed loop system to be drawn for 0 less than k less than infinity. The angle of departure between 0 to 360 of the root locus. The question is on angle of departure. The question is on angle of departure between 0 to 360 of the root locus branch drawn from the pole minus 1 plus j2. Okay, first we can calculate the exact poles and zeros. Okay, no problem. Okay, so gs is given to me. Okay, gs is given to me. What are going to be the poles of this function? Okay, what are the open loop poles? Okay, OLP. So for that, s square plus 2s plus 5 equal to 0, na? Okay, s equal to minus 2 plus minus root over b square minus 4ac divided by 2a. So s equal to minus 1 and plus minus under root of minus 16 will be j4. So divide by 2, j2. That is where there is a pole at -1 plus J2. Okay. Now, what are the OLZ, open loop zeros? I'm using some abbreviation. If you are not aware, you can note down. Okay. So, open loop 0, S square minus 2S plus 2 equal to 0. Okay. Simplify this and you will get it as -1 plus or minus J. Okay, the question is on angle of departure, and I have been telling you that angle of from root locus angle of departure, okay, is one expected 2-mark category question. Okay, so yeah, let me first draw this pole 0 configuration and write down the angle of departure here. Okay, I usually use a basic geometrical method for the angle of departure, easy only, it's very easy. So what are my poles here? Okay, my poles are -1 plus minus J2. -1 plus minus J2, and 0, sorry, will be 1 plus minus J. Okay, this is -2, now the 0 will be 1 plus minus J. Okay, 1 plus minus J. Okay, so yeah, going here. So 1 plus J, and say this is 1 minus J. And then the pole is -1 plus 2J. Say this is the pole -1 plus 2J, and then this one approximately -1 minus 2J. Okay. Now dear, the procedure I want to calculate the angle of departure corresponding to the pole -1 plus 2J. Okay, join this particular pole, okay, with respect to all the other poles and zeros. Okay, I join it first with respect to the other pole. Okay, it has to be here, I will shift it, and then join it with respect to the other zeros. This is 1 0 and this is one of the 0. Okay. Okay. Angle of departure is given by the formula 180 degree. Angle of departure is given by the formula K is positive, not a normal root locus. You have to see if K negative, then complementary root locus has to be applied. Okay, 180 degree minus phi p minus phi z. Now, what is phi z? Phi z is the sum of angles subtended by all the zeros. And how do you calculate the angle? Of course, with respect to positive x-axis. Okay, or any line passing through positive x-axis. So, let me here. This is the 1 plus j pole. Na? Okay, let me create here a line parallel to the positive x-axis. Okay, suppose this is my z1. Okay, so this is what is known as phi z1. Okay, and then okay, here also let me first create a line parallel to x-axis, and this is suppose the 0 z2, and this is the angle with respect to 0 phi z2. Correct. This 0 is 1 plus j and this 0 is 1 minus j. Okay, so phi z is actually given by sum of angles subtended by all the zeros, phi z1 plus phi z2. Now, what is phi z1? Now, this is the exterior angle of a triangle. What you can do? Okay, you can go here. Let me take this line up to here. Okay, can you calculate the interior angle of this triangle? Interior angle of a triangle by trigonometry, tan inverse height. How much is this height? Okay, this is 1, this is 2, so this height is 1, and how much is this base? Now see, this is -1 and this is +1, -1 to +1, 2 units, -1 to +1, 2 units. So this is the interior angle. What is the exterior angle? 180 degree minus tan inverse. How much height? 1, and how much base is 2? So 1 by 2 plus phi z2. Okay, 180 degree. Again, phi z2 also is the exterior angle of a triangle. So calculate the interior angle, and 180 minus this interior angle. How much is this interior angle? See the height here. Okay, 2j up to minus j, total 3 units of height, and base again -1 to 1 on the x-axis. So 2 units of base, 3 units of height. Okay, so I will write down this as tan inverse of 3 by 2. Okay. So this is going to be phi z. I will calculate. Okay, what is the net value of phi z? I will write down. Now come to phi p. Phi p is the sum of angles subtended by all other poles. Okay, but actually if you see with respect to this pole, there is only one other pole. Okay, what is the angle of this line with respect to x-axis? Here only I can see. What is the angle of this line with respect to x-axis? Okay, this angle is phi p1 for me. And since it is a vertical line, okay, vertical, perpendicular to x-axis, so this angle not to be calculated. It is known to me 90 degree. Because it's a vertical line perpendicular to x-axis. Okay, what is phi z? Okay, I will calculate this value. Okay, you can also parallelly calculate. So what is going to be this value? 180, 180, 360, and then tan inverse of half is required and tan inverse of 1.5 is required. Total 277.125. Okay, total 277.125 degree. Okay, so what is the final angle of departure? Angle of departure is given by further 180 degree minus of phi p minus phi z. Okay, so how much it is? 180 minus 90, 90, and this is minus plus 277 plus 90. It is actually 367.125, but they want the answer in the range 0 to 360. Okay, any angle you can subtract. Okay, you can add or subtract 360 because 360 means a one full rotation, you come back to the same line. Okay, so if you subtract 360, this is also 7.125. Okay, you can also write down the answer as 7.125. Okay, 7.125. Round off to the nearest integer, 7 degree. Round off to the nearest integer, answer can be noted as 7 degree. Okay, in degree they have mentioned, correct, in degree. Okay. Yes, Sampath, correct, 7.1, or you can round off to the nearest integer as 7. Done. This was a 2-mark question on the angle of departure. Okay, yeah, a fundamental question on the Nyquist plot. Okay, a fundamental question on the Nyquist plot. What is there? The open loop transfer function of a unity negative feedback system is given as gs equal to 1 upon s plus 1. The Nyquist contour in the s plane encloses the entire right half plane. Okay, the Nyquist contour in the s plane is described in the s plane encloses the entire right half plane and a small neighborhood around the origin in the left half plane. Usually in the Nyquist contour, this portion is taken this way, but no problem. Okay, some Nyquist contour is given. The number of encirclements of the point -1 plus j0 in the by the Nyquist plot of GS corresponding to the Nyquist contour is denoted as n. Then n is how much? Okay, n is how much? Dear, what is the formula for n? Now you see, what is the type of Nyquist path given? Clockwise, na? You see this direct, you see this arrow. Okay, so what you are given? You are given clockwise Nyquist path or Nyquist contour, and for clockwise the formula is n equal to p minus z. Okay, for anti-clockwise it is z minus p. Okay, so I want n equal to p minus z. What is p and z? P means number of poles of the open loop transfer function, which is only GS here. Number of poles of GS, or generally GSHS inside RHP, or inside the closed path, inside the Nyquist path given. Okay, what is the Z? Z is the number of zeros of 1 plus GSHS. 1 plus GSHS. Okay, inside the Nyquist path. In fact, when I have taken the previous session on the 1-mark question, there I have elaborated on these terms n equal to p minus z and explained you little bit more there. Okay, just writing down the now answer. What is the number of poles of GSHS in the Nyquist path? Okay, now see, GS has a pole in the Nyquist path. Inside this Nyquist path, there is one pole. Okay, very clearly that for that the picture is given. So what is the value of p? P is 1. Now Z is the number of zeros of 1 plus GSHS. Okay, zeros of 1 plus GSHS means characteristic equation is required. Roots of characteristic equation. Okay, 1 plus k upon s plus 2 equal to 0. This is what GS is given, na? K, sorry, not k, it is simply 1 upon s plus 1, simple. It is simply given as 1 upon s plus 1. Fixed value 1 upon s plus 1 equal to 0. Solving this, you get s square plus s plus 1 equal to 0. Now tell me how many roots of characteristic equation in the Nyquist part or inside our RHP? Okay, -1 plus minus. You solve this, it is simply going to be -1 plus minus j root 3 by 2. You can solve the quadratic equation. -1 plus minus j root 3 by 2. -1 plus minus j root 3 by 2. For your reference, I will locate here. Okay, -1 plus minus j root 3 by 2. What are these? These are going to be the roots of characteristic equation. Are they inside the Nyquist path? No. Are they inside the Nyquist path? No. Not inside the given Nyquist path. Okay, that means the value of z is 0. Okay, the value of z is 0. So what is the n value? P minus z. P is 1, z is 0. The answer of n is equal to 1. The answer of n is equal to 1. Number of encirclements of the point -1 plus j0 by the Nyquist plot will be equal to 1. Sampath, correct answer. On the concept, I will not call it as difficult. It's concept question, I would say. Okay then. Okay, let's be ready for the next question then. Here it is. Okay, a basic question on Bode plot, 2023 ECE 2 marks question. Okay, what is there in this question? The asymptotic magnitude Bode plot of a minimum phase system is shown in the figure. The transfer function of the system is given to you. Okay, as k s plus z power a upon s power b s plus p power c. Okay, where k, z, a, b, c are positive constants, not contents, constants. What is the value of a plus b plus c? What is the value of a plus b plus c? Rounded off to the nearest integer. Rounded off to the nearest integer. Correct? Okay, so very simple question. Basically, let's take this plot here. Okay, what is the initial slope? You see here, the initial slope of the Bode plot is -20, and initial slope is actually given by -20n, where n equal to 1. And what is this n? N actually is the number of poles. Okay, number of poles of the given transfer function. What is that transfer function? I think the name is missing. Let me write it as GS, whatever is given. The number of poles of GS at origin. Okay, number of poles of GS at origin. Now, as per our given data, number of poles of GS at origin is s power b. That means the number of poles of GS at origin is b. Okay, so for our given data, b equal to 1. Okay, b equal to 1. Okay, then you have s plus z, that is some 0 term, okay, raised to the power a. That means it may be repeated 8 times, and some pole sum power c. There may be a repeated pole repeated c times. That's what I want. I want a and c as well. Okay, so what is the pole and what is the 0? Okay, for that corner frequency. Now the slope -20 becomes 0. Here, what is the slope? Parallel to x-axis, 0 slope. Okay, so here slope is 0. This 0 is actually -20 plus 20. So I can say that their slope has increased by 20. Okay, increased by 20. That means this point has to be a 0 point. This point has to be a 0 point. Now here slope becomes -40. Okay, it was 0 and then it becomes -40. The previous slope was 0, na? That means this point is a pole. Okay, pole. But how many pole? Okay, repeated pole, because slope changes by -2 into 20. Corresponding to every pole, you know, slope changes by 20 decibel per decade. Na? Slope decreases by 20 decibel. Here it decreases by 40. Okay, so I would say about this point is, this point will represent a double pole. Okay, so what is the location of pole is not required. What I can say, there is a single 0. Okay, and you know, a value is 1. Okay, see, if I actually wanted to calculate what is the location of 0 for that corner frequency, or some other data will be given. Not required. Okay, but yeah, there is one 0 and that's a single 0, because slope changed, okay, by +20. A single 0 will make the slope change by +20. Okay, here slope changed by -40, and that is because of double pole. And double pole, now what is the power of the pole term in denominator is c here. Is c here. That means c is equal to 2. Okay, so final answer. Simple question actually. A plus B plus C, A is 1, B is 1, C equal to 2, net answer 4. Basic analysis of Bode plot. Yes, Sampath, very good, correct answer. The answer is 4. A plus B plus C equal to the 4. A plus B plus C equal to the 4. Okay, next question. Okay, yeah, very basic question only. I think the plot color changed. I don't know why this graph color changed, but okay, anyways, the magnitude and phase plot, okay, of an LTI system are shown in the figure. The transfer function of the system is, let me see whether in the video to you it is clear or not. No, I think the graph will not, okay, slightly blur, but okay, visible to you, no problem. Okay, so what is given? Magnitude and phase. Okay, I'll just come here. See what is given here. This is the magnitude plot given. Okay, the magnitude plot has been plotted with respect to log omega. Okay, this is the magnitude. Okay, how much is the magnitude? You see, it is constant. Okay, magnitude is constant. Magnitude is constant. That means there is no pole or zero term. The magnitude is constant whenever you only have the exponential term. Okay, magnitude is constant. So see, the options are there with the exponential term. Okay, but the zero term will not be there, because if there is a zero term, okay, there is a pole term, sorry, in this option number B. So there will be a slope of -20. The magnitude cannot be constant. Okay, so magnitude here, very clearly in front of you, this magnitude is constant. Okay, is constant. That means the GS function can be of the form k, and some phase is there. The phase can be because of the exponentially delaying term. Okay, exponential term e power minus st, which also represent a transportation delay, k e power minus st. Okay, or if you convert to the frequency domain, gj omega is k e power minus j omega t. Now in the decibel scale, what is given? 20 log k is 8. Okay, so from here, what is k? This is log to the base 10, so 10 raised to the power 8 by 20. Okay, I'll just find out this value. Okay, wait. And then if I talk about, this is the phase part given. Okay, this is the phase part given, and phase is given. The phase plot is only with respect to omega. Okay, it's a linear line, it's a straight line, so easy to calculate. This value given to you -60. If it is not visible, I'm making it a little bit visible to you. Okay, phase plot has been plotted with respect to omega. Okay, so how can I say the phase line? Phase line can be simply written as a straight line passing through origin. Okay, straight line passing through origin, and it's a decreasing line, so slope should be negative, minus mx. X means omega, as a function of omega. Okay, so phase is minus m omega. Okay, we can calculate the value of m. How? Okay, you can use the value of phase -60, or that is in the standard unit, minus pi by 3 is minus m into omega. What? At this phase -60 is at which frequency given? 1. Okay, that means m equal to pi by 3. M equal to pi by 3. Okay, only thing to be calculated is k here. Okay, let me do that calculation. How much is going to be the k? 2.51 approximately. Okay, 2.51 approximately. Just a second here. Just a second. Yeah. Okay. Guys, complete this calculation. I'll just take up a small call here. Yeah, okay, students. Okay, so how much is the ki calculated? Approximately 2.51. Okay, so what is going to be the GS then? Okay, almost is going to be, I have written it as e power minus j omega t. Okay, or I here the omega t is m here. Okay, so writing down the final answer, k is 2.51 e raised to the power minus j omega into t. Okay, this m means the t here. This m is what is the t here. Okay, and e power minus j omega into pi by 3. Okay, and that's what. Okay, so this is going to be 2.51 e power minus j pi 3.14 or take 3.15. So approximately pi by 3 1.05 omega will come. Okay, or 1.047. Correct. Option number D matches. Option number D matches up. Okay, it's a doubly 2 marks question 2023. Simple only. Okay, next question. Okay, so what is there? Consider a stable closed loop system shown in the figure. The asymptotic Bode magnitude plot has a constant slope of minus 20. Okay, has a constant slope of minus 20. Okay, at least till 100 radian per second. Okay, the gain crossover frequency being 10 radian per second. Okay. Now, the asymptotic Bode phase plot remains constant at minus 90 until at least till omega equal to 10 radian per second. The steady state error of the closed loop system for unit ramp input. Now, see, let me start with the Bode magnitude plot. Okay, has a constant slope. Okay, so let me consider the Bode magnitude plot in decibel space, in decibel scale for 20 log mod gj omega. Okay, versus log omega, of course. Okay, so constant slope of minus 20 at least till 100. Okay, it will have constant slope of minus 20. So I'll draw a straight line. Okay, having some constant slope minus 20 at least till 100. At least till 100. That too after 100 slope will change, but after how much time? After how much we don't know. After 100, but exactly not given. But what is next given is the gain crossover frequency. Gain crossover frequency is 10. Okay, gain crossover frequency. Let me come up here. Omega g is 10. Now see what happens at the gain crossover frequency. Gain crossover frequency is the frequency at which the magnitude mod gj omega 1 or in the log scale, okay, 20 log mod gj omega. Now what is mod? Log 1 is 0. Okay, so gain crossover frequency is the frequency at which the decibel magnitude, that is the log scale magnitude, has to be 0 dB. Okay, so I have taken a line having the slope of minus 20 decibel per decade. Okay, but there is this omega g which is equal to 10. Okay, at which magnitude has to be 0. At which magnitude has to be 0. This is some data for me. Okay, acha. What is then important is, okay, there is no slope change at least till 100. Okay, there may be some pole or 0. Okay, there may be some pole or 0. Consider this condition. Okay, so what is the GS I can consider here? GS I can consider as K upon 1 plus ST1, some poles or zeros if they are there, divided by S power 1, 1 plus STA, etc. Okay, any pole or 0 will be after 100 radian per second, because there is no slope change at least till 100 radian per second. Okay, now see why I have written S power 1 in the denominator. Okay, because this is the initial slope. Initial slope minus 20 you compare to minus 20 n. Na, to n, not repeating what is in last question only I told you, n is the number of poles at origin for GS. So n equal to 1 because the initial slope is minus 20. Okay, so number of poles at origin is 1. Now, what I want, steady state error due to ramp input for which KV will be required. Limit S tending to 0, S into GS. So anyways, if there are other poles and zeros also, when you put S tending to 0, that is not going to be required. Okay, because see S into GS, you multiply S here, this S and S will get cancelled. What is only going to be left? K into all these terms will be 1. All these terms will be 1. So only K. Okay, so what is the steady state error? Steady state error for ramp input is given by 1 upon KV, or that is 1 upon K. Can we find out the K? Can we find out the K? Okay. Now see, you can find out the K by the initial part. Okay. This is the initial part, na? You know, anytime you take initial part magnitude in Bode plot, one important formula I will give you. Okay, initial part magnitude formula for Bode plot, if it has n poles at origin, is given by minus 20n log omega plus 20 log k. Here n is equal to 1. Here n is equal to 1. So magnitude is minus 20 log omega plus 20 log k. Correct? If there are zeros at origin, then this becomes plus 20m. If there are m zeros at origin, it becomes plus 20. Okay. So now you see, okay, what I have, okay, at omega equal to gain crossover frequency, which is 10, magnitude is 0 dB. That is what is the gain crossover frequency. Now, I will just satisfy here. Magnitude is 0 is equal to minus 20 log omega. At what omega? Omega 10 plus 20 log k. Okay, so what you will say, 20 log k is 20 log 10. So value of k is 10. The value of the k is 10. The value of the k is 10. So steady state error is 1 by 10 or 0.1. Okay, because the question was steady state error due to unit ramp. So that is 1 upon kV. .1 is the answer. The phase details are given, not required actually. Okay, Bhargav, will try to plan the PYQs for APTI as well. Okay. Okay, next question. Look into this. A controller DS of the form 1 plus SKD, okay, the PD controller with the proportional gain 1, okay, is designed for the plant GS equal to 1000 root 2 by S plus 10 whole square as shown in the figure. The value of KD that yields a phase margin, this question on phase margin, and we know that phase margin is calculated at gain crossover frequency. The phase margin required is 45 at the gain crossover frequency of 10 radian per second is how much? What we need to find? The value of KD for having a phase margin of 45 at the gain crossover frequency of 10. Okay, so what is the gain crossover frequency, dear, again? At again omega equal to omega g, which is given as 10, the magnitude of the overall open loop transfer function. Okay, the overall open loop transfer function will be d of g omega multiplied by g of j omega. D of j omega multiplied by d of j omega is 1. In the absolute unit 1, in the log scale it is 0 dB. Okay, so we just have to solve this. Okay, we just have to solve this equation. Okay, so that means magnitude of, now what is ds? 1 plus skd, that is 1 plus s equal to j omega, so 1 plus j omega kd, okay, multiplied by, okay, so yeah, okay, just I'm writing this first of all, multiplied by gj omega. What is gj omega? 1000 root 2 by s equal to j omega, converting to the omega domain, upon 10 plus j omega, that is 10 plus s whole square, and this whole magnitude equal to 1. So what is the magnitude for any complex number? This is x plus j y, so under root x square plus y square. Okay, so solving it here only, the first term will be under root in the magnitude form 1 plus omega square kd square. Okay, which omega? Okay, let's put the omega also, na? Let's put the omega also. What omega? Omega can be put as 10. Anywhere you see omega, you can put 10, because this will happen at the omega equal to 10. Okay, so 1 plus, okay, 1 square plus 10 kd whole square, root over x square plus y square, okay, into 1000 root 2, numerator is constant. Magnitude of j omega is omega. What is omega? 10. Then magnitude again for x plus jy, root x square plus y square. Okay, don't take root because already square is there. Okay, so 10 square plus omega square, omega again is 10. Okay, and this whole has to be 1. Okay, so I'll copy this equation, under root of 1 plus what is left is 100 kt square into 1000 root 2 divide by 10 into how much it is? 10 square plus 10 square, 100 plus 100, 200 equal to 1. Okay, so what is there? Under root of 1 plus 100 kd square. This is cancelled as 100, 100 by 200, 2, root 2 by 2 will be root 2 shifted on the right side, only root 2 will be there. So now cancel the under root, 1 plus 100 kd square. 1 plus 100 kd square is 1. Okay, so sorry, is 2. So 100 kd square will be 1. Kd square will be 1 by 100. So the final answer kd on taking under root will be 1 by 10 or 0.1. KD answer is 0.1. The answer for KD is 0.1. Done. Okay. Next question. See, the question has some controller, okay, which is a PD controller. Again, if I have to mention that this is a PD controller, but not required. Question is on actually gain crossover frequency. Even the phase margin not required. Without this, we are able to solve it. The question is again only on the gain crossover frequency. Okay. This one question again on phase margin and gain crossover frequency, but there's a good question, better question. Okay. Consider the stable closed loop system shown in the figure. The magnitude and phase values of the frequency response of GS are given in the table. What is the value of the gain Ki? Okay, this is again an integral controller used here. Okay, for a phase margin 50 degree, for a 50 degree phase margin, what is the value of the gain Ki? What is the value of the gain Ki? Now see, again if I combine these two, these are in cascaded, what is the open loop transfer function? Open loop transfer function will be Ki Gs upon S. Okay, now you see here. So what is the net open loop transfer function? Ki Gs by S, or in the frequency domain, if you put S equal to j omega, because frequency domain table is given, so Ki Gj omega divided by j omega. Okay. Now, when you take the magnitude in decibel scale, okay, because gain crossover frequency depends on the magnitude, na? Okay, then we will come to the phase margin. Or shall I use the phase margin first? I can use both anyways. Okay, let me go to the phase margin first of all. Okay, now see, this is the open loop transfer function. Let me write down the magnitude and phase expression actually. What is the magnitude? Decibel magnitude for this. So decibel magnitude is taken as 20 log of this, and log A into B is log A plus B. So 20 log Ki, then plus 20 log mod of Gj omega, and minus 20. Okay, log A by B is log A minus log B. So divided means minus log will come, minus 20 log omega. J omega mod is only omega. This is the magnitude. And what about the phase? Okay, the phase expression of this one will be Ki is a positive real number. Okay, so no phase, then angle Gj omega will come. And denominator minus, but pure imaginary number 90 degree. So total phase is angle Gj omega minus 90. So I will first use the phase margin actually. Okay, what is the phase margin? 50 degree. Phase margin formula is 180 degree plus, okay, angle Gj omega g. Okay, angle Gj omega g means phase at omega g, the total phase at omega g. Okay, the total phase at omega g is angle Gj omega g minus 90 degree. This is 50 degree. Okay, so solving this, what is angle Gj omega g? Okay, this is 90 and 50 minus 90 minus 40. Okay, omega g is the gain crossover frequency. 180 degree plus phase of the system at gain crossover frequency. This will give you the net phase margin. Okay, so what is the angle Gj omega g is minus 40. Then I go to the table. Okay, then I go to the table. In the table mentions that the phase of the system is minus 40. Okay, at which omega? 0.5. So from the table, you are able to comment that omega g, this frequency omega g is 0.5. Okay, so if they ask what is the gain crossover frequency, that is 0.5. But what I want the value of Ki. Okay, so now what is the gain crossover frequency? We know that what happens at this frequency. At omega equal to omega g, which is 0.5. Okay, the decibel magnitude of the system should be 0 decibel. Okay, that means this is the decibel magnitude of the system, 20 log ki plus 20 log mod gj omega g, mod gj omega g, omega replaced by omega g, minus 20 log omega g. This should be 0. Okay, so now at the omega g, what is the magnitude, decibel magnitude of the system? This is already known to me, -7. You can use this. Okay, I'll substitute the data here. Okay, so 20 log ki plus this is -7 as per the table, minus 20 log omega g, which is 0.5. Omega g is 0.5. Now I have substituted the value here. Okay, so that means you see what is the value of 20 log ki? It is 7. Okay, and right side plus 20 log 0.5 or log half. Okay, 20 log half will be 6, 3. Okay. So this is going to be 6 actually. Okay, I'll write it as minus 20 log 2 and that is 6. So 27 minus 6 is 1. Okay, so what is the value of log ki? Log ki will be 1 by 20 and then final value of ki will be removing the log, taking the exponent 10 raised to the power 1 by 20. This is what you have to calculate. Okay, so let me calculate this and give you the final answer. 1.12. Okay, here the final answer is 1.12. Okay, so again a good question. Understanding of the gain, crossover frequency, phase margin has to be required. Okay, all right. Okay, so next question. Okay, consider the lead compensator of the form Ks equal to 1 plus S by alpha upon 1 plus S by beta alpha, beta greater than 1, alpha greater than 0. The frequency at which the compensator produces the maximum phase lead is 4 radian per second. Okay, so now see, what is the frequency at which the compensator produces the maximum phase lead? Okay, let me first draw the Bode magnitude plot of this. At this frequency, the gain amplification provided by the controller, assuming asymptotic Bode magnitude plot of Ks, is 6 dB. Okay. So if I want to draw the 20 log mod of k j omega, converting it to the frequency domain, okay, for lead compensator, the Bode plot will start initially with the 0 dB, then comes the corner frequency. Okay, so what is the 0 corner frequency? 0 corner frequency, time constant is 1 by alpha, corner frequency is reciprocal of time constant, that is alpha. Then what is the pole corner frequency? The time constant is 1 by beta alpha because the term is 1 plus st. Now, so you compare time constant is 1 by beta alpha, corner frequency is alpha beta. Okay, corner frequency is reciprocal of the time constant term. No? Okay, so first comes alpha, then comes alpha beta. Why? Because alpha beta greater than 1. Okay, so beta greater than 1, so alpha beta greater than alpha. So first will come 0. Anyways, lead compensator means 0 dominant. First 0 will come and then pole will come. Okay, it is clearly mentioned as lead. Okay, so 0, the first 0 will coming to slope. What will be the role of 0? To change the slope by plus 20. Okay, so initially slope 0, it will now change to plus 20 decibel per decade. Okay, plus 20 decibel per decade. Okay, then what will come? Pole will come. So this is the 0 at alpha. The pole frequency is alpha beta. Okay, and pole will reduce the slope by 20 again. So 20 minus 20 is 0. 0 slope means parallel to x-axis. Okay, 0 slope means parallel to x-axis. So this will have a slope of, I'll write down separately, 20 decibel per decade. Okay, and this will again have a slope equal to 0. Okay, the frequency at which the compensator produces maximum phase lead is 4. Okay, now the frequency at which maximum phase lead comes, okay, the frequency at which the compensator produces maximum phase lead, okay, suppose that frequency is omega m, okay, and this frequency omega m is actually the geometric mean of the corner frequencies. Okay, this is given by geometric mean of the two corner frequency, and geometric mean means, okay, under root of alpha into alpha beta. Okay, so that becomes alpha root beta. Okay, so this omega m is alpha root beta. Then what is given at this frequency? The gain amplification provided by the controller, assuming asymptotic Bode magnitude plot of Ks is 6. So at this frequency, the magnitude in decibel is 6. Okay, so there are two things. Now let's come to the calculation. What is omega m? Alpha multiplied by root beta is 4. Okay, and then this is one point, and then the magnitude here is 6. Okay, magnitude here is 6. I'll just use the slope formula. Okay, the slope of the line is 20 na, 20 decibel per decade, and slope is change in the magnitude. How much is the change in magnitude between these 2 points? You take this point and this point, 6 and 0. Okay, the change in magnitude is 6 minus 0 divided by change in log of frequency, decibel per decade, log of frequency. Okay, log of omega m divided by log of alpha. What is log of omega m? Omega m is alpha root beta minus log of alpha. Okay, so I have 20 equal to 6 divided by log a minus log b is log a by b, alpha root beta by alpha. Alpha will get cancelled. So what you are getting from here is log root beta, and that is 6 by 20. Okay, so what is the value of root beta? Is 10 raised to the power 6 by 20. Okay, this is approximately going to 20 log root beta is coming 6 na. So root beta actually will be 2. So you can then calculate beta. Beta will be 4. Okay, then omega m, alpha root beta is given as 4. Root beta is 4. So solving this, you will get alpha equal to 2. So what is the value of alpha and beta? In sequence is 2 and 4. Okay, the value of alpha and beta 2 and 4. So see, since I have taken 5 years questions, all 2 mark questions, the variety of questions you are able to see today. Okay, variety of questions that you are able to see today. Okay, yeah, this was the question. Okay, anyways, moving ahead to the next question. Okay, yeah, the state equation of a second order system is x dot equal to axt. Okay, ZIR condition, no input is applied. Okay, x0 is the initial condition. Suppose lambda 1, lambda 2 are distinct eigenvalues of a, v1, v2 are corresponding eigenvectors for constant a1 and alpha 1 and alpha 2. What is the solution of xt? Okay, see the general solution of xt. This is a standard result. Okay, so I'll just give you the answer as tick mark. The standard solution in terms of eigenvalue and eigenvector is given by the formula. The constant they have chosen is alpha 1 is given by the formula alpha 1 lambda 1. Okay, alpha 1 e raised to the power lambda 1 t into the eigenvector v1 plus alpha 2 e raised to the power lambda 2 into the eigenvector v2. That is the option number A. Okay. So whenever you study state space analysis, this is more like a standard solution, xt, standard solution of the state vector under ZIR condition. Okay, ZIR condition, because input is not mentioned. Otherwise, the equation is x dot equal to ax plus bu. So if you assume 0 input, okay, when you talk about 0 input case, then you get the x dot equal to ax. Okay. Anyways, now let's go to the next question. This is a standard result. Now coming up here, consider the state space description of a LTI system with the matrices A, B, C and D given. For the input sine omega t, the value of omega for which the steady state output of the system will be 0. The value of omega for which the steady state output of the system is 0. Now see, for input A sine omega t, see, whenever the input is of the form A sine omega t, okay, and consider the transfer function of the system as Ts, okay, the output of the system, the steady state response to sinusoid, this you study in control, this you study in signals as well. The steady state output is given by A mod of t. Now see, suppose this is sine omega naught t, suppose the frequency of the signal is omega naught, A modulus of t j omega naught. Convert this into the frequency domain and write down the frequency response t j omega. Okay, calculate the magnitude of frequency response at omega n, and then sine of omega naught t, the phase part of the sinusoid is added with the phase of the system, that is angle tj at omega naught. This is the general output formula. And what you want for the input sine omega t, the value of omega for which the steady state output will be 0. Okay, you want the steady state output to be 0. So this will be 0, okay, if the magnitude of the frequency response of the system at the specified frequency is 0. Okay, is 0. Okay, right. Frequency response can be obtained if you first get the transfer function. So this question you have to get the transfer function. Okay, you have to get the transfer function using the state space model given. Okay, now given the state space model, transfer function, method number 1, general formula. Okay, the transfer function is given by the formula C phi s into B plus D matrix. Okay, where the phi x matrix is given by Si minus A whole inverse. Okay, now here specifically method number 2 I will apply, because the given arrangement of the matrices ABC suggests that this is a CCF form. Okay, here you are given controllable canonical form. Now very important, whenever you have studied state space model, you should know about CCF, OCF, DCF and JCF. These 4 standard models, canonical models, must be known to you. This is a controllable canonical form. Okay, so you can write down the transfer function. You can directly write down the transfer function. Okay, so what is that controllable canonical form? Okay, generally I will write down the CCF form as, okay, x dot is equal to AX, okay, 0, 1 minus A naught minus A1 into X plus 0B into U, okay, and y equal to Cx, that is C naught C1 X. What are these constants? Okay, these are corresponding to the transfer function equal to B multiplied by C naught, or let me start this way, C1S plus C naught. Okay, C1 is the coefficient of S, C naught is the constant term of numerator, divided by S square plus A1S plus A naught. A1S plus A naught. Okay, A1 is the coefficient of S, A naught is the constant term. Okay, in the matrix they come up with the opposite sign. Okay, so as per these matrices given, okay, containing the method number 2 here, okay, the transfer function of the system, okay, the transfer function of the system will be how much? B. What is the value of B? 1 multiplied by, now what is this? I'll just map this. Okay, this is the B value, this is the C naught C1 value, and this is the minus A naught and minus A1 value. Okay, so what is the transfer function of the system then? Okay, C naught means the constant term, C1 is the coefficient of S, so minus 2S and plus the constant term 3 divided by S square plus A1S. Okay, so that is plus 2S and plus the A naught, that is equal to 1. Okay, and plus, now plus D. If the D is given, then the whole answer plus D. Plus D. This is the D part. Okay. So what is the transfer function of the system? Okay. What is the transfer function of the current system? Transfer function of the current system, just taking this value once again, I have 3 minus 2S. I have 3 minus 2S upon S square plus 2S plus 1 plus 1. Okay. Or rather here only, let me first simplify this. How much I am getting? I am getting S square plus 2S. Okay, so S square plus 2S minus 2S cancel, plus 1 and plus 3. S square plus 4 actually, upon denominator can be written as S plus 1 whole square, correct? So transfer function I have simplified, and my transfer function is, let's say TS is S square plus 4 upon S plus 1 whole square, converting to S equal to J omega in the frequency domain Tj omega. Now S equal to J omega square is minus omega square. So minus omega square plus 4 upon 1 plus S, 1 plus J omega whole square. Now I want mod of Tj omega. What is going to be the mod of Tj omega? Numerator is just real, 4 minus omega square, no J term. Denominator 1 plus J omega whole square. So magnitude is 1 plus omega square, root 1 plus omega square, but again whole square. And you want this to be 0. Okay, this will happen at omega equal to 2. At omega equal to plus or minus 2. Omega square should be 4. Okay, but yeah, given in the question, because it's NAT, so they have specified omega should be greater. For the input sine omega t, for omega greater than 0, okay, what is the omega at which the magnitude of the system is 0? That is omega equal to 2. That is the answer to the question. So this question, GATE 2023 2 marks question, is a good question. Okay, linking the state space analysis with the steady state response to sinusoid. For calculating the steady state response to sinusoids, I need the frequency response of the system or the transfer function of the system. Okay, but rather than transfer function, they have given the state space representation from which I can get the transfer function. General formula C phi B plus D. Okay, or here it is a CCF model, so I can use that CCF model. Okay. Now next question. Okay, next question. Now see, this is a MSQ question. I think I forgot to mention. This is a MSQ question. I will leave this as homework, guys. Okay, I'll just give you the hints. The time is already more than 2 hours of this session today. Okay, but yeah, what is the hint to the question? Consider a system represented in the state space as given to you. D by dt of x is given to you. Okay, x dot is ax plus bu, y equal to cx. Okay, which of the state space representation given below have the same transfer function as that of S? Okay, same transfer function as that of S. Okay, so first you need to calculate, little bit calculations will be involved here. First you need to calculate the transfer function of this, again by using the formula I told you, C phi B plus D. There is no D here. Okay, so only C phi B, phi again Si minus A whole inverse. Okay, first you calculate the transfer function. Okay, then calculate the transfer function of the other options and tally. But here for calculating the transfer function of the option, you will not have to go to the general formula. Why? Because option number A and C, option number A and C both are having diagonal matrices, DCF model. Okay, and option number B and D, again 0 1 minus A0 minus A1 plus no, not the D1, but the B option at least is CCF. 0 1 minus A0 A1 plus 0 BU y equal to C0 C1x. So B is at least CCF. So wherever possible, you can use the shortcuts of the CCF, DCF, OCF and JCF. D again you will have to solve by the general formula, but that you can do. Okay, that you can do. So that is why little calculative, but how to calculate I have given you the hint. For any doubts you can connect to me later. Okay. Okay, next question. Okay. Yeah, the GATE 21 2 marks question. The state space representation of a first order system is given to you. X dot is minus x plus u, y equal to x. Okay, where x is the state variable. See, it's a first order system. Okay, that is why only a single state variable will come x. Okay, and let me first draw the signal flow graph corresponding to this. Okay, the signal flow graph corresponding to this. Okay, x dot is ax minus x plus u. Now, if you take the signal flow graph, usually in the signal flow graph, the output of an integrator is assigned as the state variable. So let me take this as the integrator. Integrator gain is 1 by s. Okay, output of it is the state variable, and if output is the state variable, input is the derivative of the state variable x dot. Now x dot should be minus of x plus u. Okay, so let me create this as the input node u. Okay, so u enters here. Okay, plus u and then minus x. So from x there will be a feedback path coming, and what should be the feedback gain? Minus 1. So that how will you read this equation? X dot minus of x plus of u. Satisfied? And what is the output of the system? Y equal to x. Okay, y is directly equal to x, this state variable. Okay, so this is y. Okay, this will be unity gain. Okay, this also is unity gain. This is x dot. Correct. This is the signal flow graph. Okay, representation of the given simple first order state space model. Okay, right. Y is the control output. Now there is a control law they are introducing. Okay, let u equal to minus kx be the control law. Okay, where k is the controller gain. To have a closed loop pole at s equal to minus 2. Okay, so now with the controller in action, what will be the modified signal flow graph? Simple. What you want? U equal to minus kx. Okay, now you want u equal to minus kx. Okay. This is x dot. This is the integrator 1 by x. This is my state variable x. Okay, this was anyways unity feedback, and this was the output y. This is the original system copied. Now minus of kx, u equal to minus kx required. So this is x. Okay, taking one more branch from here, and u has to be minus of kx. So that means the gain of this branch has to be minus k. So that what will you read here? U equal to minus kx. Simply what will you read here? U equal to minus kx. This is the graph with the controller. Okay. So what is the transfer function of this graph? Can you not write it easily? Okay. What is the transfer function y by u for this graph? Only one forward path, na? Okay. Only one forward path, 1 by s. Its path factor will be 1. Because if you erase this particular forward path, both the loops are open, divided by 1 minus loop gain. What is the first loop gain? What is the first loop gain? Minus 1 by s, product of these two. Second loop, 1 by s into minus k. So second loop is total minus k by s. Both are touching each other. Both are using this branch. So both are touching. So no product term will come. Okay, simple Mason's gain formula applied. Okay, so what is the transfer function? Multiply by s throughout and you get the answer as 1 upon s. Multiplying by s, here all minus minus plus, so s plus 1 plus k. Now you want a closed loop pole at minus 2. Okay, you want the closed loop pole at minus 2. Dear, what is the pole of this transfer function? Pole is, when you solve the denominator, you will get s equal to minus of 1 plus k, and you want the pole at minus 2. Simple. What is the value of k? 1. What is the value of k? Is 1. Okay, the value of k is 1. Simple. The value of k is equal to 1. Done? Next question. Okay. Consider gate 25 ECE 2 marks MSQ question. Okay, consider a system where x1, x2 and x3 are 3 internal state signals and ut is the input signal. The differential equation governing the system are d by dt of this is equal to, again, x dot is ax plus bu. Okay, x dot equal to ax plus bu has been given to you. X dot equal to ax plus bu. Okay, which of the following is or are true? The signals x1, x2, x3 are bounded for all bounded input, whether these variables x1, x2, x3 are bounded or unbounded. See, have a look into this matrix A. Have a look into this matrix A. Okay, for this matrix A, what are the eigenvalues? Okay, because matrix A is a diagonal matrix, you can see, na? Okay, only diagonal elements are there. Okay. Okay, DCF form has been given. Because the matrix is diagonal matrix, the eigenvalues of a diagonal matrix are just equal to the diagonal numbers 2 and minus 2 and 0. Okay, so that means the poles. Now what we know that, what is the role of the eigenvalues of the matrix A? It is also equal to the poles of the control system. So the poles of the control system are 2 and minus 2 and 0. There is a RHP pole. RHP pole represents unstable system. Okay. What is the meaning of unstable system? BIBO unstable system. We define stability as BIBO stability. So this is BIBO unstable system. Okay, that means for a bounded input, it will produce unbounded output. And output depends on state variable. Okay, output depends on state variable. Okay, so if I say, okay, see, what will I say here? Let me come back there. Okay, what is the comment I will place here? Because the system is BIBO unstable, okay, that means bounded input will produce unbounded output, correct na? Bounded input will produce unbounded output, and output depends on state variable. Okay, this output, okay, depends on state variable x1, x2, x3. So if the output is unbounded, we can say that at least one of the state variable, not necessarily all, okay, at least one of the state variables is unbounded. And that actually, that also due to the RHP pole. Okay, RHP pole means x1. Okay, which of the state variable here can be unbounded? Which of the state variable here can be unbounded is x1. This corresponds to the RHP pole. Okay. So anyways, if I see the option, the signals x1, x2, x3 are bounded for all bounded input. No. There exists a bounded input such that at least one of the signal is unbounded. This is correct. This is correct. MSQ, I will just read all the option. There exists a bounded input such that the signals x1, x2, x3 are unbounded. Okay, there exists a bounded input such that the signals x1, x2, x3 are unbounded. Okay, all being unbounded we cannot guarantee. Okay, the signals x1, x2 and x3 are unbounded for all bounded inputs. No. Okay, no, only B option. It is MSQ question, but only one option matching, that is B. That is B. Okay. Dear, next question for you. Simple question, GATE 25 current year EE 2 marks question, but simple, sum of the magnitude of the poles, because I just told you poles are eigenvalues of the matrix A. Okay. Now, what is the eigenvalues of the matrix A? 2 cross 2 characteristic equation. Okay. 2 cross 2 simple characteristic equation. In my clear mathematics videos, I have explained you. Directly write down the 2 cross 2 characteristic equation as lambda square minus trace into lambda plus determinant equal to 0. Okay, so lambda square minus the trace of the matrix. Trace of the matrix is minus 3. Determinant of the matrix 0 minus minus plus 2. Okay, so what is the characteristic equation of the system matrix? Lambda square plus 3 lambda plus 2 equal to 0. Solving which you will get lambda as minus 1 and minus 2. So what are the poles of the system? Are also minus 1 and minus 2. What is the sum of the magnitudes of pole? Okay, what is the sum of the magnitudes of pole? So sum of the magnitudes of the pole, okay, will be 3. 1 plus 2. Sum of the magnitudes, so plus 1 and plus 2. So answer will be 3. Simple. This one is actually simple. Okay. Okay, dear. So with this, I have actually covered to you ECE 2021 to 25, all 2 mark question. The session went lengthy. Okay, the attendance also went down, I know, but okay. I know only few students have patience, and the few students are always the learners and the toppers and the achievers. I know that's not a big deal. Okay, the session went lengthy because, as I promised, all 2 mark question, I have actually taken all 2 marks question. Okay, combining all topics. Okay, the transient part, steady state part, root locus, Routh-Hurwitz, Bode plots, Nyquist plots, gain margin, phase margin, state space analysis. Okay, only last 2 questions. Okay, I don't want to extend the session anymore, but last 2 homework questions. Okay, block diagram and graphs, anybody can handle. Huh? Okay, so I'll give you this as homework and you please solve it. Easy one only, 23 ECE 2 marks question. Y equal to G1 R plus G2. I mean, in this question, you need to find a transfer function with respect to R input and with respect to the disturbance input. Both are easy. Okay, a simple block diagram question. This is one homework for you. And here it is, another homework for you. This one is again ECE MSQ question, ECE 2 marks 2025, but again I will give you the hint. This again they give as MSQ question, but only one answer will be correct. This is the hint to the question. Only one answer will be correct. Only and only one answer will be correct. I am not telling the answer, you have to try. That is how it is the homework. Okay, that is how it is the homework for you. Okay, dear. Okay. Okay, quick updates for all of you that, guys, the new batches, okay, the new batches for the AE examinations, okay, that is for AP and Telangana board, Transco and Discoms examination, new offline batch starts October 16th. Okay, October 16th. Okay, so if you are willing to prepare for AE, you can join the offline batch. Okay, for GATE, okay, offline batches are already in run for 2026. Okay, you can enroll into it. Okay. The fresh batches for GATE for offline will only come for GATE 27 now, because only last 4 months left. In offline, the syllabus cannot be covered now. Okay, but yeah, offline classes are still running. If you still have that enthusiasm to come and study offline, because you get the complete supervision of faculty, you can come down to the Hyderabad center and continue with the offline course, or otherwise for the GATE, you can also take the online live course available for GATE 26 as well as GATE 27. For GATE 26, 1 year validity, fees is 99.99. For gate 27 with 2-year validity, the fees for you will be 28,999. So you can enjoy learning the gate with our online live course product as well. Okay, so I will share you the PDF. I will have to share you the PDF of the control system 1 mark session also. Okay, I will share you the PDF of this as well. The password will be simple CS2. CS2. Simple. CS in small. Okay, CS2. CS for control system. C and S both are in small. Okay, so note down the password because the PDF will be password protected. Okay, right. If you are learning, if you are spending that much of time, to watch and learn, okay, then I think the notes are useful for you. For that reason, password protection is there. CS2, C and S in small. Okay, that's it, guys. We'll see you in another session. We'll try to plan similar session for signal and system as well. Thank you. Stay safe and take care of yourself.